Hi, my name is Ben Carver, and today I'll be giving a presentation on our research project, InfiniStore Elastic Serverless Cloud Storage. The performance of modern data-intensive applications, including data analytics and machine learning apps, is highly dependent upon storage. There are a variety of storage options, from high-performance in-memory key-value stores like Redis to high-performance file stores such as EFS and FSX. There are also relatively inexpensive cloud object stores, such as AWS S3, which are good for long-term permanent data storage. The myriad of storage services available complicates resource management and app deployment, as the characteristics and properties of the different storage services vary widely. This choice is further complicated by the varying memory and storage requirements of heterogeneous cloud workloads. Data-intensive applications have highly dynamic and heterogeneous workloads that benefit from storage elasticity. These charts show the working set size and aggregate throughput of two such workloads: a cloud object store workload of the IBM Container Registry and a serverless application workload of Azure Function Blob Accesses. Both workloads exhibit a highly variable working set size with a maximum size of over 209 times and 173 times larger than the minimum size for the container image workload and serverless application workload respectively. Additionally, the working set size is shifting every minute. Such significant temporal working set size variance suggests that a high degree of elasticity at the storage level is required to be able to serve the objects in the working set efficiently without excessive storage over-provisioning. The container image workload also demonstrates bursty I/O characteristics. Looking at the figure on the right, we can see that the aggregate throughput spikes to 15 gigabytes a second with an average throughput of about 1 gigabyte per second. This throughput variability poses a significant challenge for tenants trying to provision storage resources that meet the application's performance requirements. There is one more challenge if we would like to scale the storage. Storages such as an in-memory KV store can provide more bandwidth by adding more nodes, but newly added bandwidth is not instantaneously usable. The data in storage must be repartitioned and rebalanced. This causes massive data movement. To effectively evaluate the different storage options with respect to their elasticity, we define a new metric, elastiput, or elastic throughput. Elastiput is defined as throughput over latency. It is common to use a latency throughput plot to visualize how latency and throughput evolve as the number of concurrent requests increases. I will play an animation that will illustrate how elastiput changes with throughput and latency. Holding latency fixed, you can see that elastiput will increase as throughput increases. Likewise, as throughput decreases, elastiput decreases. This illustrates the direct relationship between elastiput and throughput. Now, holding throughput fixed, we can see that elastiput decreases significantly as latency increases. Likewise, elastiput will increase as latency decreases. This illustrates the inverse or indirect relationship between elastiput and latency. I will play another animation that will illustrate how elastiput changes with throughput and latency in a sort of real-world example. This example will help to illustrate why throughput alone is insufficient, and further why using a single metric that considers latency and throughput together is advantageous. In this example, we see that throughput increases while latency remains approximately fixed. This trend continues until a storage bottleneck is hit in the system on which the graph is modeled. When the bottleneck is hit, the system throughput reaches a ceiling and latency begins to increase rapidly. As you can see, the value of the elastiput metric begins to drop considerably once latency begins to increase, even though throughput is still increasing and hasn't completely leveled off yet. Cost is another important metric for users of cloud storage services. If we now take storage cost into consideration, then we can use elastiput per cost to evaluate the cost effectiveness of existing cloud storage options for a data-intensive workload. The large chart here plots storage system capacity against elastiput per cost, and then in the top right, we show a throughput versus latency plot for different types of storage systems. I'll also show the elastiput for the type of storage system that I'm discussing. First, cloud object stores, such as AWS S3, fall behind in cost effectiveness due to higher latency. Alternatively, in-memory key-value stores offer a better elastiput per cost due to their lower latency. However, the cost of storing an entire dataset in an in-memory key-value store is prohibitively high. This is why in-memory KV stores are often used to cache hot data, which achieves a balance between performance and total cost. In this case, a common technique is to profile the workload and find a sweet spot between maximizing hit ratio and cache size. This approach significantly improves cost effectiveness. We can easily find workloads that have a 100-fold difference between a full storage footprint and an effective cache size or working set size. Our InfiniStore framework employs a two-tiered design that improves elastiput per cost. InfiniStore's fast and fine-grained elastic serverless memory layer provides good elastic throughput, and the inexpensive cloud object store layer stores the whole dataset at low dollar cost. With the fine-grained elasticity that serverless functions can offer, InfiniStore achieves fine-grained proportional capacity and bandwidth scaling, which, if depicted on the plot, we see a constant high elastoput per cost regardless of the working set size changes. In contrast, I also show the elastoput per cost trends of in-memory key value stores and cloud object stores here. As you can see, InfiniStore achieves a significantly higher elastoput per cost regardless of the working set size, especially when compared against the alternative storage options. We will explore the reasons behind InfiniStore's cost effectiveness later in this presentation. Finally, InfiniStore's serverless memory layer uses a sliding window memory management mechanism to avoid data migration on scaling. Before I describe InfiniStore in detail, I will first go over some additional background info. InfiniStore is built atop InfiniCache, which has two primary components. First, there's InfiniCache's client library, which is incorporated directly into the client application. Objects stored in InfiniCache are encoded with the Reed-Solomon erasure coding algorithm to decrease latency and boost fault tolerance. The erasure coding procedure is performed by the client library. Second, there's InfiniCache's client daemon, which is responsible for function management and request routing. The client daemon forwards requests to serverless functions, which store the user data in their local memory and establish TCP connections to the associated client daemon. In InfiniCache, the memory of serverless functions is pooled together, and data is dispersed across all functions, resulting in capacity limitations and high overhead during scaling operations due to data repartitioning. Also, InfiniCache provides limited data durability, only sufficient for cache-based purposes. In contrast, InfiniStore approaches function memories in a unique way. You can conceptualize the memory within each serverless function instance as disaggregated memory pages, analogous to those found in programming languages and virtual memory. We collectively refer to the provisioned memory across all active serverless function instances as a serverless memory store. Like InfiniCache, the serverless memory store periodically invokes functions to keep functions alive. We propose a sliding window memory management policy in serverless memory to achieve elasticity. Let's see how the sliding window memory management works in this following illustration. As mentioned earlier, the serverless memory store views the collective function memory as a continuous memory space of serverless functions. Each function is identified by a global unique Lambda ID, and functions are organized into function groups. The size of these groups is dynamic and is decided by the erasure coding configuration of each request. For now, you can think of function groups as if they are one serverless function with a lot of memory. Data is appended to one side of the memory space. Given that fast platforms offer virtually infinite memory capacity, new function memory is allocated if more memory is needed. This is achieved by simply invoking additional functions. Inspired by Mark compact garbage collection algorithms, live data is marked and asynchronously compacted to one side of the memory space. As shown on the slide, an object visited by a GET request is considered to be live and is asynchronously moved to the latest function group. The client daemon performs garbage collections on a fixed interval in order to free up unreferenced data. Data that has not been accessed for a configurable duration h is considered to be unreferenced. In this example, we set h to 30 minutes. In our evaluation, h is set based on the working set size of the workload. Recall that when an object is accessed, it is moved to the most recent function group. This implies that objects in older function groups created at least h minutes ago have not been accessed and thus can be released. Specifically, the entire function group, including all serverless functions in that group, are released. Releasing memory does not require any explicit action on our part. We simply stop pre-warming the serverless functions to be reclaimed. We refer to one garbage collection cycle as a GC bucket. All functions created in a single GC cycle are considered to be in that GC bucket. GC buckets created within the last h minutes are referred to as active. InfiniStore guarantees data availability for the active GC buckets, performing 1-minute periodic warm-ups and using a parallel recovery fault tolerance mechanism to be discussed later. To ensure a smooth transition between active garbage collection buckets and released garbage collection buckets, we introduce an intermediate stage known as degraded garbage collection buckets, during which we downgrade the warm-up interval to 5 minutes, and it's important to note that no data availability is guaranteed if functions are reclaimed during this period. To handle bursts, either because of increasing concurrency, a throughput burst, or insufficient function memory, InfiniStore will scale out functions by function groups. After one function group is full, new data is inserted into the next newer function group. A new GC bucket will be created every GC cycle. Functions not full during the last GC cycle will be inherited by the newly created GC bucket. We next introduce how we achieve durability with our parallel recovery mechanism. Insertion logs are used within serverless functions to record write operations. These logs, as well as data chunks, are asynchronously persisted at the Cloud Object Store. The client daemon uses persistent buffers to implement strong consistency without having to wait for data to be fully persisted, thereby improving throughput. Upon detecting function reclamations, logs are loaded from the Cloud Object Store and replayed in the recovery functions. Chunks are restored after the log is replayed. In our experiments, we configure our lambdas with 1.5 gigabytes of memory in order to balance the number of CPUs and network bandwidth available. However, restoring 1.5 gigabytes of data will take about 19 seconds, as shown on the slide. We use 20 so-called recovery functions to restore a deterministic fraction of the total chunks in parallel. As such, each recovery function takes about 0.85 seconds to restore its portion of data. We reserve 10% of memory for recovery backup, meaning functions have 1.35 gigabytes of memory for data storage. Read requests are routed to recovery functions during the restoration procedure. The expected delay for any chunk request is sub-second at worst, but in practice, the expected delay is even lower, based on our data capacity utilized in our experiments. To evaluate the elasticity and cost-effectiveness of InfiniStore, we replayed 2 workloads on our AWS Lambda implementation of InfiniStore. We replayed the first 50 hours of trace data from the original 75 days of the IBM Docker container registry traces. For the serverless Azure Blob Access workload, we selected 5 hours of the most bursty traces from among 37 serverless applications. In this plot, the 1-hour working set sizes of the 50-hour IBM workload are depicted as the background. The working set size varies from 6 gigabytes to 40 gigabytes. The x-axis is the 50-hour lifetime of the experiment. The green, red, and blue lines show how the number of functions in the active, degraded, and all GC buckets change, respectively. Notice how the increasing and decreasing of the total number of functions matches the working set size changes. The Azure Access Blobs workload can better illustrate how the number of functions changes in correspondence to both requests and bandwidth bursts. In this chart, the IS-RPS is the throughput achieved while replaying the workload with InfiniStore, and WL-RPS is the original workload throughput as recorded in the traces. I marked a few bandwidth bursts here. These are request bursts. One of them is a burst of both bandwidth and requests. Now, if we add the number of total functions used during the Azure experiment, we can see that the function bursts can match the bandwidth and request bursts as well. We also executed the YCSB microbenchmark to evaluate InfiniStore's elasticity and latency. Our baselines include Elasticache for Redis and Anna, a low-latency KV store used by Cloudburst. The YCSB driver runs on an EC2 VM with a bandwidth fixed at 50 gigabits per second. Elasticache and Anna are also configured with a maximum bandwidth of 30 gigabits per second. This ensures that EC2 will not be a bottleneck for the YCSB test. YCSB varies the number of threads used, beginning with 1 thread. The driver drives a read-dominant workload with a fixed concurrency for 30 seconds. Then, we gradually increase the concurrency to 10, 25, 50, 75, and 100. Since the workload runs for just 30 seconds, both Elasticache and Anna do not have time to scale. For a single run, the size of the object is fixed. We show the most representative experiments for the 10 megabyte objects here. We find that Anna is not suitable for serving large objects. This is because Anna needs to deserialize the object after receiving data. For Elasticache, the bandwidth YCSB can utilize is limited by the cluster bandwidth. Beyond the limit, the latency increase causes elastoput per cost degradation. InfiniStore has no such limitation, and we see no elastoput per cost degradation until the YCSB driver becomes the bottleneck. For 1 megabyte objects, InfiniStore's latency suffers from the function invocation delay. For 100 megabyte objects, our experiments show the same elastoput benefit as 10 megabyte objects. Lastly, we show the cost effectiveness of InfiniStore. This plot shows the cost-activity breakdown for the 50-hour IBM Container Registry workload. For information about the experimental configuration, please refer to the details on the slide and the paper itself for additional detail. InfiniStore used an average of 85 serverless functions to achieve a 95.8% serverless memory layer hit ratio, whereas InfiniCache must deploy 400 lambdas to store most of the data and achieve a 95.4% hit rate. Elasticache, storing the whole dataset, requires 12 VMs and achieves a hit ratio of 99.96%, whereas the finely tuned Elasticache, used as a cache, requires 8 VMs to achieve the same hit ratio as InfiniStore, so as to make for a fair cost comparison. This configuration requires extra cloud object storage in case of a cache miss. Compared to InfiniStore, we find that it was 36.4% more expensive to replay the workload with InfiniCache. The increase in cost occurs primarily due to InfiniCache's backup design. In contrast, only a small portion of the total cost of InfiniStore is used to maintain data durability in the serverless memory store layer. We also see that using Elasticache as a full dataset store is 36.3 times more expensive than using InfiniStore. Likewise, using Elasticache as just a cache is still 4.5 times more expensive than using InfiniStore. In terms of pay-per-access, over half the cost of replaying the workload on InfiniCache is incurred by maintaining data durability. The portion spent on maintaining data durability is 106% the cost of serving GET and PUT requests. In contrast, InfiniStore incurs only 26% cost overhead over the amount spent serving GET and PUT requests from the serverless memory store layer in AWS S3. With the InfiniStore work, we have implemented a multi-layer cloud storage that inherits the underlying serverless function's elasticity and cost-effectiveness properties. Specifically, we use a sliding window function memory management mechanism to achieve elasticity, and we use 2 layers of inexpensive storage with parallel recovery to achieve durability and cost-effectiveness. The InfiniStore project is already open source, and you can find it at the DS2 Lab website. With that, I conclude my talk. Thanks for watching.